What's up, guys? Welcome back to the 12 ISLs of Christmas. Today, we're going to be stepping things up a difficulty in light of the new year, and we're going to be discussing 2021 problem N4. And here's the problem. Let R be greater than 1 and it's a rational number. Alice plays a solitaire game on a number line, and initially, we have a red bead at 0 and a blue bead at 1. And here's a blue bead. And in a move, Alice chooses one of the beads and an integer k. And if the chosen bead is a x and the other bead is a y, then the bead x is moved to the point x prime, satisfying this equation here. And we want to find all R for which Alice can move the red bead to 1 in at most 2021 moves. So this is 0 and this is 1. So let's see if we can understand this equation here, because that seems to be the heart of the problem. So we can rearrange it to suppose x prime minus y over x minus y equals r to the k. So it seems like we're just comparing the distance between the two, which is signed. So the difference between the red bead and the blue bead should realistically always be some power of r, because we keep on multiplying this by a power of r. In other words, we keep shifting one bead at a time such that the distance between the two is a power of r. And it must be a positive power of r so that the blue bead remains to the right of the red bead. So for instance, we could move the blue bead to 1 over r so that the distance is 1 over r. Or we could move the red bead to 1 minus 1 over r over here, so that the distance is 1 over r as well. So how can we get started on this problem? Well, the first thing that really stands out to us is this k here, because k can be anything. And when we keep varying the factor k that we use, we can just keep changing things as we wish. So we want somehow this r to the k factor to be invariant somehow, or equivalent to 1 or something like that in some manner, so that these two are always related in a fixed manner. And that requires for there to be some sort of thing going on. And we can study it rather well. So, and what better way to make this happen than if r to the k is equal to 1 in some sense? Because if r to the k is equal to 1 in some sense, then these two would be equal, and therefore the distance between the two is always the same. But then we must move 0 to 1, and things might become an issue. Who knows? Anyways, we have that r to the k equals 1 in some sense, but r is greater than 1. So how can we make this happen? Well, here's the main issue. R is a rational number, so we can write r equals p over q. And then we want p over q to the k equals 1. So that when we rewrite the sides, we get p to the k minus q to the k over q to the k equals 0. So we want p to the k equals q to the k somehow. And we can also see this by multiplying both sides by q to the k. And this must hold for all k, so what better way than to make p equals q? But we can't really have that happen unless we look at things modulo some prime, or some number. So suppose that p is equivalent to q mod a. Then that means that r to the k is equivalent to 1 mod a, which means that x prime minus y is equivalent to x minus y mod a. But then when we cancel out the y, we get x prime is equivalent to x mod a. So that means that the red bead is always at some sort of number that is 0 mod a, which is a rational number. It doesn't need to be an integer. But if we want to move the red bead to 1 from 0, then we must have 1 is equivalent to 0 mod a. But a is an integer, so that requires a equals 1. Otherwise, we run into issues. So that means that we cannot have p is equivalent to q mod a for any a greater than 2. So the only way we can have this happen is if p minus q has no factors greater than 1, which means it must be 1. And that requires p equals q plus 1, and therefore r equals 1 plus 1 over q. And this is the first part of our problem, because that reduces our search space a lot, because now we know r equals 1 plus 1 over q. So now that we know this, we can try experimenting with this. So first, we can try playing around with some moves and see how we can get this to work. So one move would be, for example, to move the red bead closer to the blue bead or further, but that would make the red number really ugly. So we want to try moving the blue bead. And let's try moving it further by just one factor of r. Then we get that this blue bead goes to this point here, which is just 1 plus 1 over q. And therefore that the distance is just r. But now we can just move 0 closer to make the distance 1. So we can get rid of that and make it this point here so that the distance is 1. So that's 1 over q. But look, we moved the red bead to the right by 1 over q units in 2 moves. So we can just continue inching to the right in this way, and we eventually reach 1 in 2q moves. Because for every single 1 over q units we move, we must inch the blue bead to the right and also the red one. So we want this to be less than or equal to 21. So 2q is less than or equal to 2021. I meant 2021 instead of 21. So that means that q is less than or equal to 1010. And that means that all r equals 1 plus 1 over q, where q is less than or equal to 1010, they all work by this inching forward process. Now we just need to show that if this is true, that 2q moves is the best we can do. In other words, does there exist a better strategy to go forwards than this inching forward strategy? To do so, we can try turning back to our invariant idea. Because remember how when we used r equals 1, then this just simplified really nicely and the red point was invariant. But with this r, we cannot make it equal to 1, because that would cause 1 over q to be 0, which is bad. So what is the best thing we can do than a multiplier of 1? Well, since we're multiplying and we can't make it 0, and if we had it to be equal to 2, then it's still very uncertain. So the best thing we can do is move it by a factor of -1. So we want this to be -1 somehow. So equivalent to -1 mod some number k, suppose. Actually, I'll not use k because we're repeating terminology, so I'll just say L. Then that means that when we multiply both sides by q, q plus 1 is equivalent to -q mod L. So 2q plus 1 is equivalent to 0 mod L. And this is a nice positive number, so might as well just set L equals 2q plus 1. So therefore, we can take things mod 2q plus 1. So that means that we get x prime minus y is equivalent to either x minus y mod 2q plus 1, and we're also using r equals 1 plus 1 over q. Or we have x prime minus y is equivalent to y minus x mod 2q plus 1. In the former case, we have x is equivalent to x prime mod 2q plus 1. And that just doesn't change the position of x modulo 2q plus 1. And in the second case, we get x prime is equivalent to 2y minus x mod 2q plus 1. So either we're keeping one bead fixed, or we are reflecting it across the other bead when working mod 2q plus 1. This drastically simplifies the problem for us because now we only have two options instead of infinitely many here. So let's see how we can use this to finish the problem. We start with red bead and blue bead, which I'll go ahead and order as 0, 1. And now we're working mod 2q plus 1 for the rest of the problem, because it seems like this might work. So on every single move, we reflect one bead over the other. So we look at all the possible places we can go to. So we can either reflect the first bead over the second, which gives 2, 1, or we can reflect the second bead over the first, which gives 0, -1. And we can just keep repeating this. We get 2, 3, 4, 3, 4, 5, and so on and so forth. And then over here, we get -2, -1, then -2, -3, and then so on and so forth. So, and basically this range here is where we can get after 3 moves. And we can't go any further because the reflection idea prohibits this. Now, what do we want from the red bead coordinate? Well, we want it to be 1 mod 2q plus 1 because we want it to be 1. But 1 is not an even number, as we're seeing here. So we want it to be, suppose, 2q plus 2 mod 2q plus 1, or -2q. And let's see how we can get to 2q plus 2. Well, we need 1, 2, 3, 4, and all the way until there. To get to 2, we need 1. To get to 4, we need 3. To get to 6, we need 5, and so on and so forth. So in order to get to 2q plus 1, we need 2q. In order to get to 2q plus 2, we need 2q plus 1 moves at least. On the other hand, to get to -2q, to get to -2, it takes 2 moves. To get to -4, it takes 4 moves, and so on and so forth. So this will take 2q moves to get to. In all cases, it requires at least 2q moves to get to a number that's equivalent to 1 modulo 2q plus 1, which means that the number of moves in order to move the red bead to 1 is at least 2q. And this basically proves that q is less than or equal to 1010, because this must be less than or equal to 2021, and that requires q is less than or equal to 1010. And we have shown that these q work earlier when we use the inching forward. So what's the main takeaway on this problem? Well, in order to solve the problem, we noticed that we had a very loose factor of k here, and we couldn't really control that much. And this leads to the first main inside of the problem, and it is to control what seems free in some way. And this way could be an invariant, as we found in the problem here, or it could be something else entirely. In this case, an invariant worked really well because by setting r to the k equals 1, in some way that we only figured out later, could we get this to work? And that means that we got a lot of R to not even get the red bead to 1 ever. And then for those R that works, then we need to somehow construct it and play around. And this brings us to takeaway number 2 is play around a lot. Because by playing around, you can get a sense for what values of R work and the main process involved. Because just by playing around, you can get the constructions for the values of R that work. And also, but to motivate the R to the K equals 1 approach, another way to think of it is you can experiment, for example, with R equals, suppose, 5 over 3. And notice that the numerator of x is always 2, is always even. And that can never get it to 1. So those are the 2 main takeaways from this problem. And other than that, we just use a bunch of standard modulo p stuff. And by looking at modulo 2q plus 1, we could solve the problem.